All right, chemistry class, welcome to this test review session. In this instructional video, I'm going to walk you through what you need to know for the upcoming test. And this test is going to cover chapters 2 and chapters 4. Okay, I'm actually going to use the note sheet packet that we pass out, that we go through in class. And if you have that, you can pull that out to make sure that you understand the material. And I'm just going to highlight the things that are going to be definitely tested and asked of you come the next test. Okay, so if you have that out, or just a notebook, a piece of paper, you can jot these things down. You can go back and review, ask questions if you don't understand, but this is going to be a great resource for you to prepare for the test. If you know these things that I'm going to share with you, you'll be fine. Okay? All right, in chapter 2. Chapter 2 was all about matter and change. You should know, you have to know that we were looking at different properties of matter. Okay? All matter has certain characteristics, and we're able to then categorize it or characterize it or classify it based on those different characteristics or properties. And if you remember, we looked at chemical and physical properties, which we'll talk about. Okay? These properties, the properties, we can talk about them either being extensive, you have to know this word, or intensive. So let's just give some examples here of these two. Extensive properties, they depend on the amount of matter that you have. So for example, mass, that property, that mass is going to change depending on how much you have. So that's called an extensive property. Volume as well. The volume of matter is going to change depending on how much you have. You have a little, small mass, small volume. You have a lot, large mass, large volume. Okay? So these types of properties depend on the amount that you have. Whereas intensive, you can kind of see this prefix here, they're inside the matter. It doesn't matter how much you have, a lot or little, the property is going to be the same. So for example, the density. Doesn't matter if you have a large piece of iron or a small piece of iron, the density of iron is a constant. It never changes if it's pure iron. Okay? So those are, excuse me, intensive property. Others, boiling point. It doesn't matter if you have a lot of water or a little water, it's going to boil at the same temperature. Melting point. Those are intensive. They are part of the nature of the matter. It doesn't matter. It doesn't matter. It doesn't matter how much or how little you have. Okay? A substance, again, this is just some terminology here. Substance, we refer to substance as having a definite composition. Right? And has a unique set of properties. So don't get too hung up on the terms here, but we talk about matter. Matter is everything. A substance here is a little more unique in that it has a definite composition. Okay? So H2O, that is a definite composition. It's always going to be 2 hydrogens to 1 oxygen when they combine. Okay? Then we spend a lot of time talking about physical properties. These are properties that you're not going to change the substance. You're not going to alter it into something new. You're just going to use maybe some observation skills, or some descriptive words, or some properties, the ways that maybe this behaves in a certain manner, but you're not changing the substance. You're not changing, do not change the substance composition. For example, I mentioned boiling point. Boiling point is a physical property because when water boils, it's going from a liquid to a gas. But the chemical makeup is still H2O. H2O is a liquid, H2O in the atmosphere as a gas. It's still H2O. You haven't changed the chemical makeup of water. So boiling, like melting, those are just physical properties. At what temperature does it boil? At what temperature does it melt? Okay? Physical properties, they are things that we observe, and you have to know that the substance's chemical composition is not changing. It's not changing. Okay? You rip a piece of paper, it tears easily, it's still paper. You hammer a piece of aluminum into a flat sheet, it's still aluminum. Okay? All right. The different states of matter, you have to know, I'm sure you know this already, solid, liquid, and gas, and you have to know their properties. You should know that a solid has a definite shape and a definite volume, like a block of metal, block of copper. Definite shape, definite volume. A liquid has a definite volume, like a glass of water. The water that's in there, you can measure its volume. But that water, if you pour it into a different container, it's going to take the shape of its container. Okay? Gases, they expand until they fill the container that they're in. So they have a varying volume and a varying shape. They just take on the shape of the container because those particles have higher energy and they're moving all over the place. And they'll bounce off the inside of the container continuously. Okay? So you have to know the difference between solid, liquid, and gas as far as the nature of their volume and shape. Okay? Physical changes, let's just expand on that a little bit. The identity of a material does not change. We said this already, does not change during a physical change. So you can alter a substance quite a bit, but still have the same substance compared to what you started with. So I already mentioned a number of them: melting, boiling. Okay, if you just cut something or break something, these here, often sometimes if you do something to a substance without changing its chemical composition, you may not be able to reverse that process easily. All right, if I cut my hair, it's going to be hard to take that same piece of hair and put it back on my head. That's, even though it's still hair, it's going to be hard to reverse that. Okay, but some things are reversible. Melting, if I melt something, I could easily reverse that by freezing it. If I boil something, I could easily reverse that by cooling the temperature down and condensing it. So you need to know that there are some physical changes that are reversible, others that are really hard to reverse, even though you still have the same substance before and after that change. Okay? All right, that basically was section 2.1. All right, properties of matter. Let's go on to section 2.2. In section 2.2, we continue our discussion about matter, and now we start to classify matter into different types. Okay? So, you should know in 2.2 we talked a lot about mixtures. So a mixture is just a physical blend of two or more components. So a mixture, if I take salt and pepper and I mix them together, you could have a lot of salt and a little pepper, or a little pepper, or a little salt and a lot of pepper. It doesn't matter, you get to choose. That can vary. But the mixture is two different components that are mixed together. Okay? They're not bonding, they're not forming something new, they're just mixed. All right? And when we talk about mixtures, we like to mention that some mixtures are heterogeneous and some are homogeneous. What that means is heterogeneous means it is not evenly or uniformly mixed together. So for example, if you had muddy water, you might have a container with muddy water, but you might have a lot of dirt at the bottom. You might have some things floating on top. You might have some things suspended in the middle of the water. It's not evenly distributed. Okay? Homogeneous means you mix something up so thoroughly, so well, that it's basically all the same throughout the mixture. Like salt water or sugar water, assuming that it's all dissolved. You would not be able to tell any difference if you were to take a sample from different locations of your homogeneous mixture. We also call, you must know this, a homogeneous mixture is also called a solution. Evenly distributed. Everything is evenly spread out, and basically the distribution makes it so uniform that it's the same throughout. Okay? Now, we also talked about separating those mixtures. For example, we talked about filtration, distillation, ways that you can use properties, physical properties, to separate things in a mixture. Another way we could separate is using magnetism. If something's magnetic and something is not in a mixture, okay? These physical properties, we use those in a mixture to separate the different components that are in that mixture, okay? So if you have, for example, uh, a mixture where the particles are different sizes, you can use a filter to do that. By the way, you do that, let's say you cook pasta, okay? Here's a simple example. You cook pasta, you pour the pot of water and pasta through a strainer, it catches the pasta, the water passes through. That's filtration because the large pasta is caught, the small water particles pass through, okay? If you were to have something dissolved in water, those particles are going to be so small that they're going to pass right through the filter paper. Whereas the particles that are larger are going to be trapped by the filter paper. That filtration process, it is separating based on size of particles. You need to know this. The filtration is using what property? The size of the particles. The smallest particles pass through, the larger particles get trapped by the filter. Okay? So that's what they're saying here is solid. The solid obviously is going to be trapped by the filter. The liquid is going to pass through. Okay? And anything dissolved in that liquid if the particles are small enough. Distillation we talked about as well. Remember, distillation is using the property of boiling point. So if the boiling points are different in a liquid solution, then you start to raise the temperature. The first liquid that has the lowest boiling point is going to start to boil off, turn into a vapor, and then you cool it down and separate it, cool it down, it turns back into a liquid, and you can collect it. And then you keep raising the temperature, and then the next liquid will start to boil, and you cool that down and collect it separately and continue to do that. So a liquid solution, a mixture of different liquids, can be separated by distillation. Okay? One is boiled off one at a time. Okay? So you must know these different ways to, there's our picture of distillation. If you remember, we talked about this right here and the whole process that occurs. Here's the boiling. The first liquid starts to boil, turns into a vapor, follows the tube down here. In this section right here, it's cooling down and turning back into a liquid, and you collect it. And then the next liquid, and once all this is gone, you remove that, put it in another flask, you boil it, next one turns into a vapor when it reaches its boiling point at a higher temperature, and you continue that process until all the liquids are separated. Okay? So you must know how we classify mixtures and how we're able to separate mixtures using different physical properties. Okay? All right, let's go on to 2.3. All right, in section 2.3, we continue our discussion about matter, but specifically now, we're going to divide matter into elements and compounds. On the periodic table, those are all the elements. You should know by now that elements have one type of atom, and that atom retains the properties of that element. A compound is a combination of two or more elements. A mixture would be, a mix of elements like our atmosphere, oxygen, hydrogen, helium, nitrogen, or a mix of even compounds. If I mix a bunch of compounds together, salt and sugar, or it could be elements and compounds. Take salt and you mix it with water. That's if salt water is a mixture. That's a homogeneous solution, homogeneous mixture. So mixtures are taking elements and combine with other elements, or elements and compounds, or two compounds, or three compounds. But now we're just talking about elements and compounds. Elements are pure substances that have one type of atom in them. Compounds are pure substances that have two or more types of elements bonded together in them. Okay? So element would be like hydrogen, oxygen, nitrogen, all those on the periodic table. Compounds now would be water. Elements, two elements, hydrogen, oxygen, bonded together, and so on. All of those elements are on the periodic table. So I don't remember if we did this in class, but you are going to become very familiar with the periodic table. Okay? It shows information about the elements. The vertical column is called a family or a group because they're going to have similar properties. Elements are placed on the table by increasing atomic number. The atomic number is the number of protons in the nucleus. A horizontal row is called period. And each element is represented by a symbol. And that symbol could have one letter, like hydrogen, or it could have two letters, like helium. The second letter is not capitalized. Okay? For elements and compounds, here are some things that you must know. You have to be able to tell me what an element is, and you have to be able to tell me what a compound is. Okay? They have some distinct differences. An element is the simplest form of all matter. And we have about just a little over 100 discovered elements. All matter is made up of those 100 elements. Right? And each element has a set of unique properties. A compound is two or more elements that are bonded together. They're holding on to each other, and they have completely different properties than the elements that they came from. Okay? And they have to combine in a definite proportion. So to make water, you have to have two hydrogens and one oxygen. Always. Twice as many hydrogen atoms as compared to oxygen atoms are in water. Always, always, always. If not, it's not a compound of water. Okay? A compound, you can break that down. You can take water and break it back down. You'd have to do kind of a chemical process, but you can break it back down into its elements. Right? An element cannot be broken down into something simpler that has properties. Elements are the basic substances in our world, right? And even one atom of that element retains its properties. All right? A compound can be broken down into its component elements by a chemical change. So I can pass electricity through water and break it apart into oxygen and hydrogen and oxygen. Okay? We talked before about physical changes. Well, anytime you do something, you change the chemical nature of something, that is a chemical change. You're talking about chemical properties. So a chemical change produces new kind of matter. You must know this. You have to know that a chemical change is producing something new, different than what you started with. Okay? The chemical composition is much different from the original substance, the original matter. Okay? Also, as I mentioned, the compound, it has unique properties. So water has unique properties, but those properties are much different than the elements that it came from. Water, liquid, we drink it to survive, right? Hydrogen is a gas at room temperature. Oxygen is a gas at room temperature. Very different. But when they bond, they take on a whole new personality. It's pretty remarkable. That's how we're able to get hundreds of thousands, if not millions, of different substances with their own unique properties in this world. That's fantastic. All right? All right. As I mentioned before, we mentioned this earlier, a substance and a mixture, while I may use those terms interchangeably, technically, a substance is something that has a fixed composition. Okay? It has a fixed ratio in which the things are mixed or the things are combined. All right? A mixture can change. So for example, I'm going to use this example again. H2O is a substance. You always have to have 2 hydrogens to 1 hydrogen. 1 oxygen, sorry. 2 hydrogens to 1 oxygen. But if I'm just talking about salt water, okay, I can put in a lot of salt in the water or a little salt in the water. That's up to me. That can vary, that can change. Okay, those don't have to be in a set ratio to make salt water. On the periodic table, you're going to become very familiar with the periodic table and how to read the information in that periodic table. So you should know, I'll give you a quick example here. All right. Every box on the periodic table is for an element, and that element has a symbol, a name. The number above it is its atomic number. That's the number of protons in the nucleus. And it has an atomic mass. And remember that mass for carbon, I don't know, it's exactly something like this, 2.01. Remember that mass is the weighted average of all the isotopes of that particular element. We'll talk about isotopes in a little bit. So chemical symbols represent the elements and chemical formulas represent compounds. So each element has its own symbol. Remember, some symbols can be one letter, some are two, and if you combine those elements into a compound, then you bring those elements together in a chemical formula. So for example, carbon dioxide. There's carbon and two oxygens bonded together to make carbon dioxide. There's two elements there. There's a symbol for carbon, there's a symbol for oxygen, and these small numbers down here, I don't need to write the one. Those small numbers will tell me the ratio in which they combine. Okay? So one or two letter symbols for the elements, chemical formula for the compound. It tells us what what symbols. The symbols are going to tell us what elements are involved, and the subscripts, the small numbers, are going to tell us how many atoms of each. It's telling us the ratio in which they combine. Okay? This periodic table, which is going to be your best friend, it helps us organize the elements, and they are always, right now, our modern periodic table, it's organized by increasing, you must know this, increasing atomic number. That is the number of protons. All right? And they also are organized, instead of just listing them all in a linear fashion, there's rows and there's columns, and that's because everything in a column has similar properties. Notice right here, repeating properties. Why do we go to a second row? Because everything in that first column has similar properties. So everything in the first column, also called family, you must know everything in a column have similar properties. They behave in a similar manner. Okay? So everything in group 1, those are all alkali metals. Those metals all act in a similar manner. Everything in the last group, the last family on the periodic table, all those inert gases, noble gases, they all behave in a similar manner. Okay? So right here it says, if they're in the same column, a group is a column, they have similar physical and chemical properties. You must know that. We'll talk about some of those. And why do they have similar properties? We'll talk about that coming up. Okay? And I already mentioned that they are organized by increasing atomic number. All right? So, a little introduction to the periodic table. You're going to learn more and more about the periodic table, and not just that it is just a list of elements, but it's organized in a specific manner to help us distinguish things. Remember, everything in a column is a family. They behave in a similar manner. You'll realize that metals are on one side, non-metals are on the other side. You'll realize that the shape of the periodic table has to do with how the electrons are arranged around the atoms. We'll save that for another time. Okay? All right, let's go on to the next section here as we continue our test review. Okay, in section 2.4, we looked at chemical reactions. Okay? You must know in a chemical reaction, new substances are formed. Always. Now, there are things that we can look for to determine if a chemical reaction occurred, and we're going to talk about those. But the only way that you can definitely be certain that a chemical reaction actually has occurred is to test what is produced after and notice that it is different, it has different properties than what you started with. It has a different chemical composition, different chemical makeup than what you started with. Okay? So chemical reactions are going to involve chemical changes. You must know, this is the key right here, chemical changes. And important thing is, during that chemical change, even though new things are produced, you have not destroyed or created any new matter. You have conserved mass. The total mass that you started with is equal to the total mass after the reaction. Very, very important point. All right. During the chemical change, the composition of matter changes. Not the mass, not the total mass, but the nature of the chemical nature of the substance is going to change. Okay? And chemical change must occur for chemical properties to be observed. So now we're talking about chemical properties, and we did a whole lab on chemical properties. Was a gas produced? Did there a color change? Was there heat given off? Was there a precipitate formed? Okay? Lots of evidence that you can use to determine whether there was a chemical change, and now we have new chemical properties because we have completely different matter, different substances. Okay? When you have a reaction, remember, whatever you are starting with, it could be multiple elements, it could be multiple compounds, it could be an element and a compound. Whatever you're starting with, you're going to try to see if they react. Those species, those substances are called reactants. Then the reaction occurs. We draw an arrow that shows change, yields, produces, and they are going to produce something new. It could be one element, one compound, multiple compounds, multiple elements. Those are called your products. Okay? Those are your products. What you start with are reactants. What you end with are products. And they are going to be different. They differ in composition, they differ in their chemical properties, they differ in their physical properties probably, and they're going to be completely different. Something new has been produced from whatever your original substances were. Okay? As mentioned, we look for lots of clues that a chemical reaction has occurred. What are those clues? Well, the change in composition is really the only true way to confirm that a chemical change has occurred. But there are clues that we use, and they could be some type of energy transfer. So that is heat, light. So if you see an explosion, or you see a flame, or you see smoke, or it feels warm, or it feels cold, possibly there's been a chemical change. Okay? There could be a color change. Something could change as far as the color of it. Not a guarantee, but a clue that maybe a chemical change has occurred. You might see bubbles. There might be a gas produced, all right? Or there might be a solid produced. Remember, we call that a precipitate. So all of those, you need to know these clues right here and be able to maybe identify them or list them or know that they are evidences for a chemical reaction, a chemical change, okay? And then the last part of this was we were talking about the conservation of mass, which basically means even during a chemical reaction, even if it's violent, a violent chemical reaction, you are not going to create or destroy matter. Whatever you started with is going to be existing after the reaction. It's just going to be arranged differently. What actually happens is when a chemical reaction occurs, bonds are broken. Things are ripped apart, pulled apart, and now they're free to rearrange with other things in that reaction and form something different. Rebond with something else. Okay? And you're going to have a totally different substance. So, during that process, though, the total mass before and after does not change. That is called the conservation of mass. Mass is neither created nor destroyed during a chemical reaction. I showed you in the lab a very violent reaction. Doesn't matter how violent it is, what you started with is what you're going to end up with. but it's going to be totally rearranged. Okay? During chemical reactions, the total mass of the reactants equals the total mass of the products. Now, if we don't capture all of the products, it might be hard to mass them and compare to what you started with. So for example, if some products are gases and those gases escape into the atmosphere, now you've lost some of the mass from that reaction, and the mass of the product that is left behind, maybe it's a liquid or a solid, is not going to be equal to the starting mass because you lost some of the product. It went into the atmosphere. So, but if you trap everything and you capture all of the products, the total mass of all your products is going to equal the total mass of all your reactants. Okay? Mass is always conserved. It doesn't matter if it's a physical change or a chemical change. Mass is always conserved during that process. Okay? You boil water. If you trap all of the water vapor and mass all of that water vapor, even though it's going to expand out, that's going to be the same mass as the water that was boiled off. Okay? You're not losing matter. You're not losing substance. It's just changing either its form, or like in a physical change, it might just change its form from a liquid to a gas, or it might be changing its chemical composition. Chemical change, remember, bonds are broken. Now they're free to go find something else, something new, and form a new bond and form a new compound, or break apart a compound into its elements, but making something different than what was there originally. Okay? All right, so that is basically what you need to know for that section. So far we've covered chapter 2. Okay? You might want to pause the video here and just go back and review those sections, see if you have any questions, jot down a few extra notes or whatever you need to do, because we're going to move on to chapter 4 now and talk a little bit about that. All right, as we dive more now into chapter 4, we're going to focus a little bit more on the atom. Remember, the atom is the basic building block of all matter. It is the individual particle that retains the property of that, the smallest particle that retains the property of that element. Okay? So, it's very important. Isn't it amazing that something so small is so critical, so valuable? So atoms are the fundamental building blocks of all matter. Amazing. All right? These were not discovered until, maybe some scientific, technological discovery was found, because we needed something powerful enough to observe what we thought probably was there based upon some experiments. So early on, you had philosophers like Democritus here was proposing that matter was made up of small indivisible particles, but he didn't know for sure. It wasn't until John Dalton came along in the 1800s, and John Dalton made the first theory based upon scientific work and scientific evidence that basically that atoms are the basic building blocks. They're the smallest particle of an element, and they're all going to be the same. Every atom of an element is going to be identical, except for, as we'll learn, maybe the number of neutrons or the number of electrons. But the nature of that, the properties of that, are going to be the same. All right? So Dalton had this basic theory, and you need to know the main components of this theory. All right? We talked about this actually. Let's go down to the question where we talked about this right here. John Dalton's atomic theory basically said what? All elements are composed of tiny individual particles called atoms. All right? And that each element, the way this is stated is wrong. Each element is composed of one type, just one type of atom. All right? That was the one that did not meet the criteria. Atoms of different elements can physically mix together or can chemically combine in simple whole number ratios. They always are going to combine in the same ratio. Okay? And then chemical reactions occur when atoms are separated. Remember I said the bonds are pulled apart. They're pulled apart. They rearrange themselves, or maybe they are apart already and they're going to then come together and they're going to bond. All right? But atoms of one element are never changed into atoms of another element by chemical reaction. In other words, a carbon atom doesn't magically turn into an oxygen atom. Okay? If you have it bonded with something, it can pull apart and then bond with something new, but you still have carbon before and carbon after the reaction. Remember conservation of mass? You don't lose those atoms. They're the same atoms before and after. They just get to be rearranged. Okay? So you need to know the major components of John Dalton's atomic theory. Atoms are extremely small. Obviously, we do have technology now that can kind of observe those atoms using an electron microscope. The atom is the smallest part of an element that has its properties. We mentioned that already. Okay? All right. So that is just kind of an introduction to the atom here in section 4.1. Let's go on to 4.2. In 4.2, we're diving into the atom and we're kind of picking it apart. We're looking at the components of the atom. What is inside the atom? Now, we're only going to go as deep as the 3 major subatomic particles, but scientists are finding more particles. We don't know how far they're going to go. Maybe there's an infinite level of going down to, inside the atom and inside the nucleus and whatever. Okay, they're finding particles that are called quarks and neutrinos and smaller particles even than that. And maybe there's no limit. Okay, doesn't seem to be a limit to how big our universe is. Maybe there's no limit to how small our universe is. That's pretty incredible. All right. So an atom is made up of a nucleus. Now the nucleus is the core of your atom. That's where all the mass is. That's the dense part. And then there's a bunch of space. Most of the atom is space. Here's a remarkable thing. Most of matter is space. Even something that is solid, it appears to be solid, it's mostly space because the atom has a small nucleus and then lots of space around it. That's where the electrons are. Okay? But it has a very dense nucleus in the middle. That nucleus is where you've got your protons and the neutrons. Those are in the nucleus. That's where the dense core is. And then the electrons are somewhere outside of that nucleus. We'll talk about maybe where they reside, where they hang out later on. But that's pretty phenomenal, that most of the atom is empty space. That should blow your mind. It's just that small, dense nucleus where the protons and neutrons are that carry most of the mass, almost all the mass, and then a big cloud of space where the electrons hang out. That's crazy. All right? You need to know the different parts here. You need to know where the electrons are outside the nucleus. You need to know that electrons have almost zero mass, nearly no mass, a little bit of mass, but almost zero, and we give it a -1 charge. It has a charge of -1. Protons are inside nucleus. Has a mass that we equate to being 1 atomic mass unit. That's called an AMU. So 1 atomic mass unit is the mass of a proton. And a proton has a +1 charge. Okay? Neutrons are also inside the nucleus. They also have a 1 AMU mass, and they have no charge, 0 charge. So you'll notice the charges are from the electrons, negative, and protons, positive. The masses are from the protons and the neutrons. Okay? Now, how were these things kind of discovered? Well, In class, we will have talked about, we talked about the electrons and how they were discovered by Thomson here, those charged subatomic particles. So you need to know a little bit about Thomson's discovery with the device that he used to discover electrons, their charge, and their mass. So make sure you know that. Okay. You need to know. You don't need to know that Goldstein discovered the proton, but you just need to know that it has a positive charge on it. Okay. And then later on, the neutron was discovered as well. All right. I do want you to understand one experiment in particular. Okay. Specifically, this experiment I want you to understand, and this was Rutherford's gold foil experiment. We talked about it in class. Okay. So Rutherford's gold foil. All right. Make sure you understand that. That's basically when he was shooting a ray of particles through gold foil, and most of them just passed right through, and every once in a while one would ricochet off. And that was the theory then that came from that is matter is mostly empty space, that an atom is mostly empty space, but it has a core dense nucleus. That's what was ricocheting the particles. Okay? So from these different discoveries, they started to create these models of what an atom looks like. First, the model was, well, the atom is kind of like a bunch of positive and negative charges, kind of like in a bowl of pudding. All right, what's called the plum pudding model. All right, but later on, the model became a core, a dense core nucleus, and the electrons around that somewhere. And that was the result of Rutherford's gold foil experiment. All right, leading to the idea that the atom is mostly empty space. Again, that should blow your mind. The atom is mostly empty space, but look at all this matter around us that's solid. It's mostly empty space. Okay, containing what? Small, dense, positive charged core. That's your nucleus, and then the rest of the space is where the electrons are. But they're so small and packed together so tightly that we have solid material, all right, with a considerable amount of density. All right, so you need to know that the protons and neutrons are at the center of the atom in the nucleus. The electrons move around the nucleus in some fashion, and we'll talk about those locations in an upcoming chapter. Okay? All right, let's move on to our next section here as we continue our discussion about the atom. Okay, atoms of an element are identical as far as their properties. There are slight changes though, and we're going to talk about those changes now. The mass and number of protons is basically how we identify an atom of a particular element. Okay? Now the number of protons never changes for an atom, for the atom of an element. But the mass of an atom of an element, those masses can change slightly because the number of neutrons can change. So let's talk about that. Okay. As mentioned, atomic number and mass number, those are kind of the identity of every element, an atom of an element. Okay? That basically is telling us the number of protons, that's the atomic number. Atomic number is the number of protons. The mass number is protons and neutrons together. Let me say that again. Atomic number is number of protons, just number of protons. The mass is protons plus neutrons added together for that particular atom. Okay? So every element has a unique atomic number. Every element always has the same number of protons in its atoms. Carbon atoms always have 6. Always 6. Oxygen always have 8 protons in every atom of oxygen. Always. Hydrogen always has 1 proton. Always. Every atom of hydrogen has 1 proton. That is the best way to identify it because it never changes. Okay? That's the number of protons. Mass can change slightly because the number of neutrons can change, not dramatically, in an atom. Okay? The number of neutrons can be found by subtracting the atomic number from the mass. So if you know the mass of a carbon atom is 13, and you know that carbon has an atomic number of 6, then that particular carbon atom must have 7 neutrons. Okay? So carbon has several isotopes. Isotopes are atoms of the same element, but they have different masses. Why? Because they have different number of neutrons. Not protons. Protons are always the same, but neutrons can change. So you might have carbon 12, carbon 13. Okay? You might have a lot of carbon 12 in nature. That's probably the most prominent one, most abundant one, and a little carbon 13. And you're going to take the weighted average of that in order to find the overall average, the weighted average for carbon. That's why on the periodic table, the masses are decimals. They're not whole numbers, okay, because you're taking a weighted average. Most elements contain several different isotopes that differ in the number of neutrons and therefore will differ in the mass of that atom, okay? Isotopes are atoms of the same element, but they have different number of neutrons and therefore different masses. They behave just like every other element, or every other atom of that element. Chemically, they're exactly the same. They have the same properties, okay? And that's because they have the same number of protons and electrons. They're going to behave exactly the same. It's just their mass is slightly different, okay? Let's scroll down here for a second. And let's look at this and just confirm that we would know how to do this. So we did this in class, but I just want to review. All right. So if you know hydrogen, there's the symbol for hydrogen, and the atomic number is always 1. Every atom of hydrogen has 1 proton. Always. Okay? 1. Always. And if it's neutral, it is also going to have 1 electron. Okay? Helium, there's the symbol He, its atomic number is 2. It's always going to have 2 protons. And if the atom is neutral, it's going to have the same number of electrons, and so on. Okay? But let's come down here to this one. When we did this one in class, I just want to remind you, okay? If you have hydrogen, it has 3 different isotopes. Okay? Hydrogen 1, what is that 1 telling us? The 1 is telling you the mass. So hydrogen 1, it actually is called hydrogen. Okay, that's hydrogen there. Hydrogen 1 has what? 1 proton, 0 neutrons, and a mass of 1. It has to have 0 neutrons because the proton is always there and it has a mass of 1. Okay? We're supposed to match up these names, so I'm going to kind of go follow just the arrows here. Hydrogen 2 is called deuterium. All right? Actually, that's fine. Here's deuterium. All right? Deuterium has 2 protons. Sorry. I messed that up. Always has 1 proton. But its mass is 2, so it must have 1 neutron, because the protons plus neutrons gives me my mass. Okay? Hydrogen 3, called tritium, it's going to come down here. It always has 1 proton because it's hydrogen, but it has a mass of 3, so it must have 2 neutrons. Okay? So by comparing the protons, which never changes for an element, and the mass of that isotope, you can then find the number of neutrons. Protons plus neutrons gives you mass. Okay? And then if we were to find the weighted average, we'd have to be given, it would have to tell us what percentage of all the hydrogen in the world is hydrogen 1? And we would use that percentage along with its mass, and the percentage of hydrogen 2 along with its mass, and the percentage of hydrogen 3 along with its mass to find the weighted average of hydrogen. Okay? Okay, so atomic mass, the atomic mass of an atom is its actual mass, based on the actual number of each type of subatomic particle. Remember, the mass is what? Protons plus neutrons. The atomic mass of an element is a weighted average. It's a weighted average because you've got isotopes. They have different masses, and they are in nature in different percentages, different abundance. So it's the weighted average of the mass of all the isotopes of that particular element. The atomic mass is measured in atomic mass units. All right? And the atomic mass of an element usually is close to the mass of its most abundant isotope. So as I mentioned, if carbon has a weighted average of 12.01, then probably the most abundant isotope of carbon is carbon 12. Okay? Carbon 12. Now, remember the way we can kind of denote how much we have, okay? So remember, we can write the symbol like this. This here is the mass, all right? That's the mass. And this here that is the protons, or the atomic number. Okay? So if you see a symbol like this, you've got your symbol for neon, and I believe this gives you a lot of information. So then what can you do is, you could also find the number of neutrons, because what you would do, the number of neutrons, even though it's not in the symbol here along with your numbers, this top number, when it's written like this, that's your mass. The bottom number is the number of protons, but the number of neutrons is going to be the mass minus the atomic number. So you know the number of neutrons here is 12. Okay? So you can find the number of neutrons. All right. We are going to continue this discussion as we dive further into the atom. We are going to be talking about also not just the neutrons and protons, but we're going to spend a lot of time talking about the electrons, because those are very important when we look at the bonding and the chemical reactions that occur. Okay? All right. That basically is what you need to know for the test. Chapter 2, Chapter 4, and that is a great summary right there. If you want to watch this video again, it might be a good idea. Or pause it, jot some things down, go back, review, maybe do some more questions in the note packet or in the book. You know, ask questions. If you have questions of me, I can help you. But use this tool, this resource here, to get ready for the Chapter 2 and Chapter 4 test. It'll be together, one test. Okay? All right. Keep up the good work. Let me know if you have any questions.